All right, so here is our last section for Newton's laws. This one is about free body diagrams. I already showed you a little bit about this, but I want to go into a bit more depth on what free body diagrams are so you can use them, since you have to, in the next unit, make some equations based on your free body diagrams. For example, F net equals winners minus losers. It's important to know your winners and your losers and what direction they're pointing in order to figure this out. So our purposes for today, we want to learn about force notations. So what are the symbols that you need to use for that? And how to draw free body diagrams. That's very important. So here is a list of a bunch of forces. We got notation, we got description. So we've got FG, you know this one, force of gravity, easy. We have force applied, is written like this. That's any push or pull that is applied to an object. Technically, I guess force of gravity is an applied force. It's applied specifically by gravity. But we will put force applied for stuff where you're pulling an object or you're lifting an object or stuff like that. This one's kind of like a generic, this is an applied force. And we have FF, this is force of friction. Force of friction is just a force that opposes motion based on the interaction between two objects. You should know what friction is. Here's the normal force that we talked about before, Fn, not to be confused with F net. Fn is normal force. If it's F with an net, that's the net force. So don't confuse those two. That's very, very important. So normal force is the support force that is perpendicular to the surface. So if you have a surface like this is the normal force. It's applied upwards. It's what causes your objects not to move through a surface. And then we have T. This is tension. So this is a force caused by a rope or a chain. Essentially, it's something that's just a pulling force, not a pushing force. So you can't push something with a rope or push something with a chain. You always have to pull that. Then we have FE. We don't use this one as much. We'll use it a little bit in next unit. So this is elastic force. This is with springs or with elastic bands. This is where you distort an object and it wants to return to its original position. Last is F air, which is air resistance. Again, this one we don't use a lot. It's really hard to calculate, so you probably won't see this very much. And usually we're going to ignore air resistance unless you're told otherwise. So these are all the different notations. You must know these. I am not going to tell you what FG is or FF. You need to know what these mean and how to apply it into a free body diagram. All right, so first example here, we've got a box is pushed on a rough surface at a constant velocity. Anytime you hear the word rough surface, automatically you think there has to be friction. So here is our box. It's by a square. We draw it by a square. We've got force of gravity down. We've got normal force up. Those two forces are always going to be there if you have something that's on a surface. We've got a force applied. And we've got force of friction since it's rough surface. Now, something that's very important with free body diagrams. You need to have the arrows the proper sizes. And I could do this on the computer easily because I can make sure that they're exactly exact. When you are drawing this, you probably won't be able to make it exactly the same. I don't want you having a ruler and measuring exactly the same. There's an easy way for you to draw this out. So for example, this is moving at constant velocity. That means all your forces are balanced. So Fg and Fn are equal. So we put two lines on it, and that indicates these two lines are the same. I'm going to do the same for force applied and force of friction, but I can't put a single line there because force applied will not equal force normal most of the time. So I'll put double lines on these to indicate that these two are equal. So the double lines are equal to each other and the single lines are equal to each other. So if you're not great at making sure lines are about the same, put these there so I know for sure that you think that those are equal. Let's do a skater gliding on frictionless ice at a constant velocity. Here's your skater as a box. You've got force of gravity. You've got normal force. These two are balanced. So they are like this, and that's it. So here's an interesting thing about free body diagrams. This free body diagram looks like the same as an object sitting on a surface. Remember when we talked about the water bottle sitting on the table? It was the exact same diagram. So free body diagrams don't tell you if you're moving. This object's moving. There's no applied force. They're just moving across a frictionless surface. This is Newton's first law. A skater in motion without friction or a force applied will keep going at a constant velocity. We cannot tell motion based on the free body diagram. We can only tell if there's acceleration or a change in velocity. That's the only thing you can tell. Let's do a car that's accelerating from rest, so it's speeding up. Box, force of gravity, force normal. You should get used to those by now. Anything that's on a surface, these two are there, and we're not accelerating up or down, so those have to be balanced. There's a force applied, and there's a force of friction, because cars have friction. So because we're accelerating, the force applied has to be bigger. If I was decelerating, I'd make force of friction bigger than force applied. Or in this case, I've got a car slamming on the brakes, so there's no applied force. We're just, think of it as your tires have stopped moving, and so there's just friction acting on your car. So FG, F normal, those are balanced. And we've got a force of friction that's causing our car to come to a stop. No applied force in this case. Another example, we have an object falling through the air, so I take an object and drop it. All we got is FG, no other forces. Technically, yes, you have air resistance, but unless I tell you otherwise, ignore air resistance. It's only in some cases that we're going to deal with that. Another example here, we've got an airplane speeding up, so it's getting faster. We have acceleration. That tells you your forces have to be unbalanced. And it's speeding up sideways while flying. So here's our box. We've got some forces here, force of gravity. We're going to have an upwards force, which is F lift. So lift force whenever we're dealing with something flying. So we have a bigger force going sideways, a slower force. Let's call this one air friction. And then that's going to be your free body diagram for this one. So that's the end of this unit. We have covered all of 3 Newton's laws. We have figured out what free body diagrams are, so how to draw those forces acting on an object. From here, moving on to the next unit, once we get there, we're going to look at more specific forces. Force of gravity in more detail, force of friction, force elastic, tension. We're going to look at these a lot more clearly in the next unit. Now it's just figuring out what the concepts are. So on your test, be ready for concepts and being able to describe situations using Newton's laws. That's how you need to picture things. So I had to throw in another Marvel movie into this. This one's from Captain America Civil War. Take a look, figure out what you think is not correct in this one. There you go. So try and think what is not correct with this. Okay, so you might think I'm going to talk about the fact that it's impossible for you to stop a helicopter from going, even if you have biceps as huge as Captain America. Let's give him the fact that he's superhuman. He's got strength. He's got the ability to hold the helicopter. That's actually not the part that I wanted to talk about, because I'm going to say that that part is, well, I'm just going to say that that's not the part I'm talking about. The part I actually wanted to talk about is the fact that he stops the helicopter from taking off in the first place. So if we watch this, it's specifically this part here. So the helicopter is taking off. He jumps onto it. The helicopter pulls down a little bit. Okay, that's realistic. That makes sense. But he's now somehow managing to hold the helicopter down with no grip at the bottom. So if you look at this, he's pulling down. There's no way here that he's able to hold on to this. Okay, he's pulling down on the helicopter. Even if he's got superhuman strength, he's not anchored onto the roof at all, that helicopter is still able to pull up, right? There's no longer this jerking downwards because there's additional mass. It could now pull up no problem, and as Captain America is trying to pull down on the helicopter, remember the helicopter has this reaction force that pulls up. He's actually going to pull himself up instead of pull the helicopter down. The helicopter has way more mass. It's not going to accelerate, so therefore Captain America must be going upwards. So there's the actual part I wanted to talk about. Holding back the helicopter, yeah, that's not true. That part we can all recognize as incorrect, but this is the part that additionally does not make sense.